All right. So we got this this riverboat, and riverboat problems are a classic way to talk about relative motion. Relative motion is a conversation about one thing moving relative to another thing. Well, you know what? Maybe we just jump into it like this. If I've got a boat, I can label this as an overhead view of a boat. Okay, so I'm looking at a boat from overhead, and I've got water. I can zoom in on this just to make it easier to see. Looks like I got a little house, I've got a dock, I've got a couple trees, maybe even a little picnic set there. But it seems to me that if this is water and we're calling this a river, the water is going to be flowing in a certain direction. And of course, like anything in these vector scenarios, we want to have a reference frame. So we could say, all right, we're going to have north, we'll have south, we'll have east, we'll have west. And just to be difficult, let's make south be positive and west be positive. Not to be difficult, just to show that sometimes it makes sense to choose different things. I would say south is positive because the water looks like it's flowing that way. Making west positive is maybe a little bit arbitrary, but maybe we could talk about the boat going from one side of the river to the other side of the river. You know, like say that we're going to cross from the house over to the side where there's no house. I don't know, whatever. Anyway, when we talk about a general equation, and sometimes I have students that go to talk with tutors, and they'll come back talking about a general equation for relative motion. And I'll zoom back out, I'm sorry. And when I talk about this general equation for relative motion, I'll write out the full version, okay? And then we're going to use abbreviations to shorten it up. Because I think if we write the full version, and you'll see what I mean in a minute, it just takes up too much space. So they'll say something like, all right, so we talk about the velocity of an object, and then they write a dot. And I'll tell you about the dot in a minute. Stationary reference frame. I'm just going to say stationary frame. And by the way, everything that I just wrote out there is a subscript. And so when I say we're going to come up with some abbreviations, it's because this is a heck of a subscript, right? Like, it's too much. It's too much for us to deal with. But I do want to quickly draw attention to this dot, because when I read this dot for a velocity statement, the dot gets read as the words relative to. Okay, so what I'm writing when I write this statement with the subscript is this is the velocity of an object relative to a stationary reference frame. In the context of the boat's the object. The stationary reference frame includes the shoreline, the house, the trees, all that stuff that's sitting still, stationary. Okay? So in this context, that's what it means. And then I can say, okay, well, that's going to be equal to the velocity of the object. Remember, this dot means relative to medium in motion. And in the context of the story that we're telling right now, the object still is the boat, and the medium in motion is what? The water. The water is the medium in motion, right? So that's why I say this is a general statement. And then we say that value plus the velocity of, I'm going to shorten things up or else I'm going to run out of paper and you will too. I'm going to shorten medium in motion to just medium relative to, and even the stationary frame I'm going to shorten up to the word stationary, because I have run out of space on this page. And that definitely draws attention to the fact that these subscripts are just too big. They're too big, they're unwieldy. And so what people will often do is they'll shorten them up and they'll do something like this. Velocity of object relative to stationary is equal to the velocity of the object relative to the medium plus the velocity of the medium relative to the stationary. And that's a little bit more manageable. Now, as we write that out, I want to point out we said on a previous day that when vectors get added, and all of these velocities, really and truly, they're vectors. When vectors get added, visually we talk about tip-to-tail vector addition, that alliterated thing. Tip to tail, and we talk about it as snapping together like Lego pieces that have to snap together in a certain way. Notice in the subscripts that one of these vectors finished with an M and the other one started with an M. That's the notational way of indicating tip-to-tail addition, okay? So there really is like a writing way of doing this. This is the notational way in the subscripts of showing that tips have been added to tails, okay? I'm just drawing attention to that. You don't have to draw in that bracket there, but I just want to make sure that it's visually like really obvious that we're not saying anything new here. We're just coming up with a way of writing what we've already said. Now, in our specific context, if that was the general way of writing things, in our specific context, we would talk about the velocity of a boat relative to the shore. And that being equal to the velocity of the boat relative to the water plus the velocity of the water relative to the shore. And again, in my common sense, my experienced life knowledge, I know that if I take and I like to canoe. I like to canoe with my son, I like to canoe with my daughters, and I like to canoe with my dad. I know that if I take a boat out on the water's in motion, and if I canoe in the same direction as the water, aren't those two velocities going to add up? And even if you've never been in a canoe in your life, you can imagine this, right? You can also imagine that if you're in a canoe and you're trying to go upstream, somehow your velocity is going to be upstream and the velocity is going to be downstream, and these two velocities are going to be battling each other. So, I mean, it's still going to be vector addition, it's just that one's going to be a positive vector and one's going to be a negative vector. True? Now, what we've talked about mostly so far has been displacement vectors. Displacement vectors, I would say, are really easy to picture because it's really just looking at pathways on a map. Velocity vectors, we got to think about not just a pathway on a map, but how fast and in what direction. And so sometimes people say, oh, this is like an extra layer of abstraction. And I guess in a way it is, right? Because we can't just like picture it as like a, dotted lines on a map or something like that. We got to think about how our motion is adding up. And so that's, I guess, in a way more challenging. Oh, by the way, when people write this out, they write it as VBS, boat, shore, see? And VBW plus VWS. Okay, and again, notice that joiner is still there. The W is the joiner this time instead of the M, but it's still just as valid, okay? Now, we want to put a box around this one, and I just want to give a name to this kind of expression. This kind of expression is called a vector equation. And we talked about vector equations once before. This time we're talking about it with some meaning. Before we just talked about it in general terms, okay? All right, so I say, oh, hey, in this river, let's just say that the velocity of the water relative to the shore, and somebody might say, oh, that's the flow rate. That's the flow rate of the river, the velocity of the water relative to shore. Yeah, that would be a slang way of saying the same thing, the flow rate of the river. The velocity of the water relative to the shore is 10.0 meters per second south. That's the rate of flow of that river. And we say, hey, we're going to come up with a boat. And this boat has the capacity to move relative to the water at 5.00 meters per second. Now, I'm going to hesitate. I'm not going to give it a direction because rivers flow as rivers do, but boats are steered by human beings. And so I'm not going to give a direction to that. I'm going to say that, hey, on any given situation, any given day, I might decide to go upstream, downstream, or cross stream, or diagonal, or whatever. Okay, so I'm not going to put a direction on that just yet. I'm going to hold myself back. I want to take a look down here at the question. The question says, if the boat goes with the flow of the river, or in other words, travels downstream. So I'm trying to use different vocabulary words, just in case English isn't your first language. I'm trying to use slang, and I'm going to continue to lean into using slang to make sure that we're all speaking English as you'll encounter when you're talking with people. But if you go with the flow of the river, travel downstream, those are both synonymous terms. What direction is my velocity of my boat? South. Looks like in this situation, we're talking about a velocity of the boat relative to water equals 5.00 meters per second south. So I left it as a red question mark before. Now I want to specify, because in this portion of the story, we know velocity of the water relative to the shore is still the same thing, 10.0 meters per second, also south. And if I want to answer the question, I'm going to start off by using my vector equation, VBS equals VBW plus VWS. And I'll just start subbing in my values. Hey, south is positive. We said that in our reference frame up above. So we can say 5.00 meters per second plus 10.0 meters per second, 15 point, oh shoot. Now if I'm being a good decimal place person here, how many decimal places? Yeah. What's that? 2. Be careful. 10.0 has got 1 decimal place. This guy's got 2. If I'm doing straight up, just straight addition, 1 decimal place. 5.0 meters per second. Sorry, 15.0 meters per second. And really and truly, since that's positive, we're going to say south. I know realistically, this is fast. You ever been in a canoe and you're going at 15 meters per second? I haven't. So these are not realistic numbers. These are nice round numbers just for the sake of conversation, okay? Anybody who's an experienced canoeist knows that this is not a realistic. This would be like whitewater rafting and then some, okay? This would be fantastic. 15 meters per second. One time I was going from this lake that was up high to another lake that was down low, and there's a meandering river between the two cutting through marshlands, and it was like going down a roller coaster. It was amazing. I don't think we hit 15 meters per second, but at the other end of that marshland meandering river, there was a mother moose and her baby, and me and my friend Drew had to hit the gas, and we just paddled like heck, and we paddled between the two moose, and that was the day that I almost died, because that mother was charging us and trying to protect her baby. But I don't even think then I approached 15 meters per second, but it was a thrill, let me tell you, okay? I wouldn't have been here today if I'd paddled any slower. Anyway, therefore, the boat, I think we saw like 20 moose on that trip. There's a lot of moose on that trip. Travels at 15.0 meters per second south relative to the shore. And I would, as is my normal style, that's the easy question. That would be the easiest version of this kind of question, okay? The follow-up question is, what if the boat goes against the flow of the river? Or in other words, it travels upstream. Upstream means to go against the flow. Find the resultant velocity. Okay, well, if I'm writing out my givens, velocity of boat relative to water, in this case, is still going to be 5.00 meters per second. But what direction? North. North, honey. Velocity of the water relative to the shore hasn't changed. It's still the same river, 10.0 meters per second south. And I go to approach my vector equation, and somebody's like, well, how has it changed? This is the beauty part. The vector equation doesn't change. It's still the same vector equation. What has changed is my givens. So when I sub in my values, velocity of the boat relative to water now is going to be negative 5.00 meters per second, because north is negative, plus 10.0 meters per second. And I have been in this situation trying to, on the Grand River, trying to paddle up the Grand River during the spring melt. And when that water is going fast and you're trying to go upstream, what's going to happen? Am I going slow? Am I going upstream? Or am I going downstream?
The other way.
Yeah, look at this. Aren't I losing the battle? I'm losing the battle. And if you're on the Grand River, that's no big deal because you're going through farmland. But if you're on the Niagara River, you're going over the falls, baby. Like, this is dangerous stuff, right? You don't want to have falls behind you. So this is something contextually that you might care about. For me, this was just trying to say, maybe like more or less as not moving as possible so that Uncle Jim could fish. But I'm paddling like heck. And it wasn't 5 meters per second. It was more like, like 1 or 2 meters per second. Like something sustainable, right? Anyway, the answer here is going to end up being 5.0 meters per second. But 5.0 meters per second positive means south in this case. We're getting washed backwards. Which Might not be so terrifying if there's no waterfalls. Okay. And so we can say, therefore, in context, the boat gets washed downstream. I'm trying to use my slang here so that we all know what it means. Downstream means in the same direction that the stream is flowing in, at a velocity of 5.0 meters per second south. And I could even throw in this extra little bit relative to the shore. Then it gets a little bit more complicated. And the question says, what if the boat travels west relative to the water? Find the resultant velocity. Now, if I was going to draw myself a river, redraw the diagram at the top of the page, these squiggly lines represent the shoreline, okay? And I want to think about what would happen. Before I even math this thing out, I want to think about what the scenario is. Imagine for a second that I could turn off the water, so that what once was a river is now a pond. Follow? If I could turn off the flow of the water and just point my boat west relative to the water, my boat would do this. It would travel across the water. And if I was better, I'm trying to make these dots be equally spaced. If I'm a ticker timer kind of thinking person, constant velocity, right? Going west. And now I want to use my imagination again and say, well, what if I didn't row my boat at all? What if I had the river flowing, but I just let the boat drift, you know? If I let the boat drift, I would start off here. And wouldn't I just drift downstream, like the way the X's are marked, right? Now the thing about these vector equations is that the resultant velocity, the velocity of the boat relative to the shore, is the sum of these two things, right? The velocity of the boat trying to do its thing and the velocity of the water trying to do its thing. That's what it means to have a vector sum. And so if both these things happen at the same time, what's going to happen to the direction of the boat's travel? Can anybody like point it out with their finger, like trace it in the air? Yeah, everybody's going diagonal, right? And so I'm going to do this. Just for the purposes of this thought pattern, I would say what the boat would really do when these two vectors happen simultaneously is that they would travel off at an angle like this. And if I wanted to think in a way similar to when we were talking about throwing basketballs, wouldn't that mean that I would have X motion like this, where all of the spacings are equal, and I would have Y motion like this, where all the spacings are equal. Follow how that's similar to basketball throwing that we did earlier? That was actually kind of why we did the basketball throwing, was to set up this pattern of thinking, right? Like weeks ago. Anyway, let's write out our givens. What we're showing with this little diagram is the velocity of the boat relative to the water is 5.00 meters per second to the west. And the velocity of the water relative to the shore is 10.0 meters per second south. Now, if I was going to do it as a ticker tape dotted diagram type thing, that would look like this. If I was going to be a vector thinker, I would say, oh, well, VBW looks like this. VWS, notice I made it a little bit longer, looks like this. And the vector equation still hasn't changed from up above. The vector equation still is VBS equals VBW plus VW dot S. Here's the thing though. This vector equation does not mean, let's make sure we're really clear about this, because I think that the questions up above could confuse us. What this vector equation does not mean is 10 plus 5 is 15. It does not mean 10 plus 5 is 15. What a vector equation it tells us is take those two vectors and add them up tip to tail. Follow? Because we're talking about a vector plus a vector being added up, tip to tail. That's what this equation is saying. It's not saying 10 plus 5 is 15. In fact, what it's saying is this diagram. I'll do it in red so that it really pops. VBW plus VWS gives us a resultant of VBS. So just to be clear, it's going to go off at an angle. And to be very, very clear, you know what? I'll highlight it in yellow just to make sure that there's no doubt about it. This stuff here in yellow is the vector representation of this equation here. Cool? It's not 10 plus 15, it's tip to tail, add those vectors together. Now, if I want to go back and analyze this, I'm going to have to say, hey, if I actually want to find VBS, Pythagorean theorem. If I want to find theta, SOHCAHTOA. And I do, because it says, what if the boat travels west relative to the water? Find the resultant velocity. Velocity is a vector, so I need a direction. Velocity needs a magnitude in units, so I'm going to have to do all that stuff. I'm going to do the Pythagorean theorem in SOHCAHTOA. So I'm going to say velocity of the boat relative to the shore is equal to VBW squared plus VWS squared, all square rooted. And I can sub in my values. 5.00 meters per second squared plus 10.0 meters per second squared, all rooted. I'm just going to get this page number out of the way. And I get 11.1803 meters per second. Does anybody want to second that motion? Yeah, a few people quick on the calculators got me. And I'm going to round it off to appropriate sig figs. So 3 sig figs, 11.2 meters per second. But that's not all, because I have to get a direction because it is a vector. So I would use, what do you think, sine, cos, or tan? What's the most reliable one? Yeah? Tan, yeah. So tan theta is equal to, the opposite is VWS. The adjacent is VBW. And you can see why it would be so important for me to label things up properly here, because I want to make sure that my givens match up with my picture, and my picture is going to help me to know whether to use sine, cos, or tan, and how to sub things all together. Okay, so communication is really important. So theta is equal to tan inverse of, and I can sub in my values, VWS was 10 meters per second, 5.00 meters per second for the VBW. And I'm running out of real estate here. But does anybody have a theta value for me, unrounded? Like, give it to me 3 decimal places. 63.435 rounded. All right, 63.435 degrees. And I know that would be approximately, I got 3 sig figs, 63.4. And if I was going to have a therefore statement, I could say, therefore, the velocity of the boat, velocity of the boat was 11.2 meters per second. And then direction-wise, I could say, look, remember, west, 63.4 degrees towards the south. West, dial yourself 63.4 degrees towards the south. Now I could also say south, dial yourself, is it 26.6 degrees? 90 minus 63.4, 26.6 degrees towards the west. And our textbook would probably go with the second one because it's the smaller of the two. Okay, but they're both equivalent, and you'd get full marks on an evaluation. Now there are also textbooks, and you'll see them out there, that would say, instead of south 26.6 degrees west, they'll say something like this, 26.6 degrees west of south. That's another way of saying the exact same thing. And so I'm building this into the note right now because there's going to be people that are looking at other resources. You're looking at online tutors. You have a older brother or sister that's helping you with this stuff, I just want you to have that notation so that you can see that that's an equivalent way of talking about it, okay? 26.6 degrees west of south. And I think that'll just help people out as they're, you know, really we're all saying the same thing, but sometimes we say things in different ways, you know? It's just trying to be friendly and inclusive with all the different ways of expressing the same ideas.